Hey guys, Mr. Betts here. I want to talk to you about the fundamental theorem of calculus and how we can use it to evaluate definite integrals. So just a quick refresher. If we have a definite integral that looks like this, this represents an area in the coordinate plane, and we evaluate that area. We find that area using a Riemann sum. We started by approximating using Riemann sums, so that's like right rectangular approximation method, what I called RRAM, or left rectangles or trapezoids. And then we could make the area exact by using infinitely many rectangles, so applying a limit as the number of rectangles approaches infinity. Right now, the only way that we have to evaluate a definite integral is using a process like that. We were able to do it with infinitely many rectangles analytically or by hand with some specific functions, specifically polynomials with low degrees. But we could also use technology like a computer program or a calculator to do that for other functions. So what we're going to do now is take this fundamental theorem of calculus that we've looked at before, and we're going to manipulate it in a way that we can evaluate a definite integral. So notice that this fundamental theorem of calculus has a definite integral built into it. So what I'm going to do is just essentially take this equation and I'm going to change it in a way where we get that definite integral by itself, and then we can figure out how to evaluate a definite integral. So to start with here, what I want to do is get rid of the derivative. So this is saying if we take the derivative of this expression here, we get this expression here. So to start with, I'm going to take the antiderivative on both sides. So the antiderivative, remember, is asking the question, what did we take the derivative of to get this? Well, on the left side, we took the derivative of this to get this. Okay, so we just put the derivative operation in front of it. On the other side, we don't know what the antiderivative of this function is. It really depends on the function itself. So I'm going to call the antiderivative of this big F of x. Okay, so again, I don't know what it is, but I'm going to call it big F of x. And remember, when we take an antiderivative, there's really a constant of integration here. So I took the derivative of, let's say, for example, this is x squared. Okay, so f of x is, let's say it's 2x. So the antiderivative of that could be x squared. It could also be x squared plus 7. It could also be x squared plus 9, x squared minus pi, x squared plus any constant. So that's why we have that plus c there. Now, this is what's called a general solution. So that plus c there is saying that this is a solution to this differential equation regardless of what the initial condition is. What I'm looking for to figure out what this plus c is some initial condition, some value I can plug in for x so that I can figure out what c has to be. And if we look at the left side of this equation, there is a value that I can plug in for x, knowing that this is interpreted as an area, so that I get a value that I know, and that would be where x equals a. So if we evaluate the integral from a to a of any function, we're evaluating an area that has 0 width because we're going from a to a, which means that this area is going to be 0. So what I'm going to do in this equation on both sides is I'm going to plug I'm going to plug a in for x. So we're going to evaluate from 0 to 0. That's going to give us, I keep saying 0. We're going to evaluate from a to a, and that's going to give us an area of 0 equals the antiderivative, whatever that is, evaluated at a plus some constant. And using this, we can figure out then that that constant has to be the opposite of f of a. Okay, big F of a. So the antiderivative evaluated at a, at that lower limit. So now using that, if we plug that back into this equation right here for c, so we're putting this in for c here, we have the integral from a to x of our function f of t dt is equal to big F of x, so the antiderivative evaluated at x, minus the antiderivative evaluated at a. Now, at this point, what I'm going to do is just substitute a few things. I'm going to substitute, for the purpose of making it look like I want to, I'm going to substitute for x, I'm going to make that a b. Okay, so remember, we're looking for a process to evaluate an integral from a to b of some function. Okay, so I want to make it look like this. So x's are going to get replaced with b's. And then once I replace those x's, this doesn't have to be another variable, a dummy variable anymore. So I can replace those t's with x's. All right, so making those exchanges, we have the integral from a to b of f of x dx is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. And a convenient thing about this is, even though we had the plus c right here, it doesn't matter what antiderivative I use. Remember, any function is going to have infinitely many antiderivatives. So, for example, 2x had x squared as an antiderivative, but also has x squared plus 1 and x squared minus pi and all those other examples. X squared plus any or plus or minus any constant. It doesn't matter which one of those I choose, as long as big F of x is an antiderivative of f of x. Okay, that's what we started with here. So this process gives us another version of the fundamental theorem of calculus. So I'm going to call it part 2. You'll see some textbooks call them the first fundamental theorem of calculus and the second fundamental theorem of calculus. I'm not a huge fan of that, because that implies that they're two different theorems. Really, they're just equivalent versions of the same theorem. So I'm going to call them part 1 and part 2, but just understand that they're both the same thing, just written in different forms. So this process gives us a way to evaluate definite integrals. In fact, this is also sometimes known as the integral evaluation theorem, because it gives us a method, a process for evaluating a definite integral. So I'm going to go through this example right here at the bottom and show you how this can be applied here. So to start with, remember, big F is going to be an antiderivative. Now, it's any antiderivative. So I'm going to call big F of x x squared. Remember, an antiderivative is going to be x squared plus a constant of integration. But since it says any antiderivative, I can choose any value for c I want. I'm going to get the exact same answer regardless of what I choose for c. So if I call c pi, if I call c negative 12, if I call c e to the pi or whatever, this is going to work. I'm going to choose the easiest one, which is c equals 0, and it's just x squared then. So this definite integral is going to be that antiderivative evaluated at 2 minus that antiderivative evaluated at 1. So we plug 2 into the antiderivative. That's going to be 2 squared, which is 4. And then we plug 1 into the antiderivative. That's 1 squared, which is 1. And so this definite integral has a value of 3. This is a definite integral that we could actually evaluate using geometry. If we were to graph the function y equals 2x and go from 1 to 2, we can find the area of this trapezoid using geometry, and we would indeed get 3 for that area. But now we can evaluate this using analytical tools, processes that we did not have in our toolbox before. I do want to point out that we are not going to use this notation. We're not going to use the big F notation when we're doing this generally. So real quick, I want to go through and just show you the notation that we're going to use. So instead of writing big F of x equals something off to the side, we're just going to write it in our work, in our line of work. Remember, again, this can be any antiderivative. So if you really wanted to, you could call it x squared plus 1. I'm not going to do that. And then we're going to use the evaluation bar to show that we're evaluating that. And this is a new thing. We're going to use the evaluation bar, but we're going to show both of the limits along that evaluation bar. So what this is saying then is we're going to evaluate 2 in x squared, which is going to be 2 squared, or 4. We're going to evaluate 1 in the x squared function, so minus 1 squared, and then that gives us our answer. So this is a little bit more succinct than saying, okay, the antiderivative is x squared off to the side, and then evaluate that at the two values. So again, fundamental theorem of calculus, this new version of it, this rewritten version of it, allows us to evaluate definite integrals using the idea or the process of anti-differentiation.